It's my great honor and privilege to be selected as a winner of this year's King Faisal International Prize in Medicine. It's my first time that I visit Saudi Arabia, and it's really a privilege for me to know more about the people and the science here. So today, I'd like to tell you a story of how I became a scientist. Now, this is a photo of myself, which is over 30 years ago when I was still a secondary school student in Hong Kong. So I was very interested in science ever since I was small, especially in the science of biology, especially about this particular molecule, which of course is a DNA, which I feel somehow actually hold our fate, and also control our health and our susceptibility to diseases. I still remember that time when I was in Hong Kong, the biology textbook which I use is a textbook called Biology, a Functional Approach, which is a very interesting textbook in that every few pages, they will have photographs of famous scientists. And one of the photographs is that of Watson and Crick, standing in front of this place, which later on I realized is actually the King's College Chapel in the University of Cambridge. So I become very fascinated by Cambridge, how it could produce so many good scientists. And so eventually, when I finished my secondary school, I actually was admitted to Cambridge to do preclinical medicine. So I actually went into this college in Cambridge, which is Emmanuel College, which was about 400 years old when I was admitted. And this was the college where actually John Harvard studied before he actually went to the US. And Emmanuel is very nice in that architecturally, it has a very nice pond in which there are some ducks swimming around. And history has said that one of the teachers at Emmanuel College is somebody called Thomas Young, who actually was one day walking along the pond and actually discovered a duck playing with the water. And he noticed the wave was interfering with each other, and actually that stimulated him to design the double slit experiment, which proved that light has a wave-like property. So I think that story actually teaches me that as a scientist, you have to be very observant about your environment, because sometimes you get inspiration from environment, as I'll talk more later on. Now, in Oxford and Cambridge, if you are a medical student, they actually only allow you to do it for 3 years. And after that, you have to reapply and to see who else would take you for the remaining of your studies. So in my situation, after my 3 years at Cambridge, I then moved on to University of Oxford, and then I joined this college, which is Christ Church. And the Christ Church is actually the largest college size-wise in Oxford, and has very nice architecture. Now, for example, this is the dining hall in Christ Church, which of course now, as you might be aware, was actually converted into the dining hall in the Harry Potter's movie, okay, which is on the right-hand side. And I'll talk more about Harry Potter later on. Now, and this is a photograph of myself when I was a student in Oxford. Now, in Oxford, it's very strange, is that you have to wear a gown like this if you are going to a dinner or even for examinations. And actually, the length of the gown is related to the result in examinations. If you are a social student, then your gown will be shorter. You are called a commoner. And this, I was very lucky that actually gave me a scholar gown, which means that for that particular exam, my result was a bit better. Now, so in Oxford, I start to actually have to see patients. And I remember actually in one of my first clinic, which is a surgery clinic, I was with a doctor called Jack Collin, which actually your chief executive officer was a colleague of at Oxford. And interesting, when I was in this surgery clinic, I came across a disease called hemangiosarcoma of the rectum. Like all good medical students, when I went home that night, I decided to read up about that disease. But strangely, I could not find it in any textbook. And later on, when I went to the library, I still could not find it. It actually took me about a month to realize that this was only the 5th case of hemangiosarcoma of the rectum ever described. So eventually, I actually published this paper together with Dr. Jack Collin and a pathologist called Dr. Ken Fleming. And this was actually one of my first publications. So that story actually taught me that even as a medical student, provided that you are observant of the environment, you can make original contribution to science. So that history makes me more keen to want to pursue medical research. So then I start to actually do different rotations. And one of the rotations which I do is obstetrics. And I start to realize that when women are pregnant, they would like to know whether the baby they're carrying are normal or not. And one definitive way in which you can do that is to stick a needle into your uterus and obtain some cells from a fetus. But the problem is that every time you put a needle in the uterus, you have about 0.5 to 1% chance of harming the baby. And as a result, many pregnant mothers are very worried. So as a young medical student, I was wondering, why do doctors do so dangerous things? Can we not do something safer? For example, is it possible just by taking a blood sample from a mother, you can tell something about a baby? But of course, this thinking at that time was quite revolutionary because we all know that our blood circulation and our mother's blood circulation are separate. So how can you just take the mother's blood circulation and tell something about a baby? But as a young medical student, I thought maybe the conventional thinking might be wrong. Might be there's some sort of communication between the two blood circulation systems. Maybe some fetal cells will enter into maternal blood. But the question is, how do you prove that? So I thought about that for about 6 months. And one night, I was having dinner with a friend, and we were talking about getting married and having sons or daughters. And suddenly, I realized that if a mother is carrying a son, a baby boy, and if our thinking is correct, then the baby boy should release male cells into the circulation of mother. So if I can take the blood from a mother and show that there are male cells circulating, then we would have proven the case. So then I actually called one of the professors in Oxford and asked him, can he give me a chance to do this experiment? But actually one of them was not very positive because he said, well, if there's this phenomenon before, people would have done it extensively, wouldn't leave until you to do it. Which of course is true most of the time, but I still want to fight and go on. So I actually called another professor, and that professor actually allowed me to spend some time in the laboratory. And interestingly, after a few months, we start to actually see those cells. Now this is one of the later experiments in which we do, in which we use a dye, a probe, which will bind to the male chromosome. And if it binds, then you can see a black dot. And you can clearly see there's some male cells in the blood circulation of the pregnant woman. And interestingly, eventually we actually published this work when I just graduated in December 1989 in The Lancet. And then a few months later, The Lancet actually did an editorial about this, saying, is it a boy? Because you can use this technology to tell if the baby is a boy or girl. And then I did my housemanship. And then after that, I decided I want to, because I started this work, I want to finish it. So I decided to go back to Oxford and to do a PhD on this field. But unfortunately, sometimes in science, to show something exists is easy. To do it every day, diagnostically and accurately, is difficult. It's just like we can go to the moon in 1969, but even now, we cannot go there to tourists or even live there. And unfortunately, fetal cells in maternal blood is one of those things. Even though we can prove that the phenomenon exists, even in the 80s, but the number of fetal cells are so rare that it's very difficult to actually do it robustly. So this is a photograph of myself when I was doing my PhD. You can see that I'm completely covered, almost like as if I'm in a desert. And the reason is because I'm a man, so every cell in my body have a male chromosome, so I have to cover myself up to minimize the risk of contaminations. But the problem is that even with all that care, because the number of fetal cells are so rare, that after a lot of work, we still cannot do it. So eventually, I have to graduate in 1994. And so one of my biggest achievements in my PhD years is that I actually met my wife, Alice, who also actually is here today with me, and we graduated together in Oxford. And after that, I still want this phenomenon to work. And so I spent another 3 years on it, until 1997, but still we could not get this technology to work. So by 1997, as you know, is the year when Hong Kong actually went back to mainland China. So Alice and I thought, well, this is a good time to go home, because many people at that time were worried about the future, so they left Hong Kong. So there are a lot of jobs coming up. So we decided to actually go back to Hong Kong and then join the Chinese University of Hong Kong, which is in the northern part of Hong Kong, next to the sea, on a mountain. It's very nice, very green. And then I have a chance to look back at what I've done for the previous 8 years. What have I done wrong? Why can I not crack this field? So for the previous 8 years, I've been trying to hunt for fetal cells in the mother circulation. As I was thinking about that, suddenly I saw that 2 papers published in this issue of Nature Medicine, in which they say that in patients with cancer, the cancer cells will release DNA into the plasma of the cancer patient. And then suddenly I thought a cancer growing inside patients is quite similar to a baby growing inside its mother, except that naively, I thought that I've never seen a cancer which is as big as an 8-pound fetus. So I thought if a cancer, a small cancer, can give you enough DNA for you to see in the plasma, maybe the baby will give us enough DNA to see. So basically what we did is that for the previous 8 years, I was focusing on cells, which was wrong. And now, since I'm going back to Hong Kong, I need to start afresh anyway. So I thought there was a chance to gamble and try to look for the fetal DNA in the plasma. But at that time, I have no idea how to extract this DNA from plasma. But one thing I know is I know a little bit of cooking in the sense that in the UK, the food is terrible, as those of you who have spent time there. So every now and then, I'll go back to my room and cook Japanese noodles. So when you cook Japanese noodle, what you do is that you boil the water for 5 minutes, and then you put the noodles in. So I thought, how about if I boiled plasma just like I cooked the noodles, okay? And let's see what happens. But strangely, of that boiled soup, if I take 10 microliter of that and then do PCR for Y chromosome, I was able to get a signal in some women and no signals in others. And later on, when I follow up those women, I find a group with the signal, all those groups, all have baby boys, and the other groups all have baby girls. So I almost could not believe my eyes that for 8 years, I've been looking at the wrong part of blood. So just by looking at plasma, even with one drop of plasma, you can already get a signal. And later on, when we measure the concentration of this signal and follow over time, you can see the x-axis is the gestational age from 0 to 40 weeks, and the y-axis is the fetal DNA concentration. You can see that basically you can see fetal DNA as early as the 7 weeks, and then the concentration keep on climbing, probably because the baby is getting bigger. And then I thought, well, how much of the mother's plasma is constituted from a baby? But the answer is surprising. We find that a mean of 15% of all the DNA in mother's plasma is from a baby. So imagine the mother so big and baby so small, and yet it's working so hard to push all this DNA out in the mother's blood. And then I'm also very interested to see what happens after the baby is born. So I actually do follow some women at the time of cesarean section, up to 2 hours after delivery. So you can see that basically the fetal DNA is cleared very quickly after the baby is born. By 2 hours, most pregnant women will have the plasma gone of fetal DNA. So now we have this new source of fetal DNA, which is very abundant, like 15%. So we can now use this to do a variety of prenatal testing. And one of the first things you can do is to determine the sex of a baby. And you can use that for sex-linked disease like hemophilia and some form of muscular dystrophy. And you can also use it to determine the blood group of the baby. Because sometimes if the baby and mother's blood group are different, the mother could attack the baby immunologically. And those 2 applications are now close to 99% accurate. And actually both of them are now used worldwide in this area. But nowadays, perhaps the number one reason why pregnant women go for prenatal testing in most parts of the world is because they're worried the baby might be suffering from chromosome abnormality, like Down syndrome. And of course, as you know, each of us normally will have 23 pairs of chromosomes. But in Down syndrome individual, one of the chromosome set, chromosome 21, instead of 2, will have 3. And so after we've discovered this phenomenon, many people have asked us, can we use this phenomenon to detect Down syndrome? And the answer is quite tough. The reason why it's tough is because for sexing, you're asking if the baby has a Y chromosome or not. For blood group typing, you're asking if the baby has like the rhesus T blood group or not. So those are qualitative diagnoses. But for Down syndrome, you have to count how many chromosome 21 the baby has got, which is a quantitative diagnosis. And this counting is made more difficult because, as I told you just now, most of the DNA in the mother's plasma is the mother's own. So this mother's background will interfere with your counting of the baby DNA. So it took us 10 years to actually think of a way to do this robustly. So how do we do this? So in 2007, I thought that I would need to go back to the basics to do a thought experiment. So now we know, on average, every mil of the mother's plasma, there is the DNA content from 1,000 cells. So I call this 1,000 genome equivalents. So let's say conservatively, 95% of this is from a mother and 5% is from a baby. So it means that every mil of the mother's plasma, there are 950 maternal genomes and 50 fetal genomes. Now, every maternal genome, there are 2 chromosome 21. So you have 950, you have 1,900 chromosome 21. Now, on the fetal side, if the baby is normal, so every fetal genome, there will be 2 chromosome 21. So 50 will be 100 chromosome 21. If the baby has Down syndrome, then every fetal genome, there are 3 chromosome 21. So the 50 fetal genomes will give you 150 chromosome 21. So now imagine if you have a test which will tell you how many chromosome 21 there are per mil of the mother's plasma. In the normal situation, it's 1,900 plus 100, which is 2,000. In the abnormal situation, it's 1,900 plus 150, which is 2050. So in other words, if you can develop a molecular test which can tell 2,000 from 2050, then you solve the problem. But as those of you in the audience who work on DNA, you know this is tough because most people detect DNA using the polymerase chain reaction, which is a doubling process of copying. So you can tell 2,000 from 4,000, but not 2,000 from 2050. But however, in 2007, I also thought one way in which we can solve this problem is if you can count the DNA molecules one at a time. And you can do this if you have a very sensitive PCR, which can detect single DNA molecule. And I thought that the more molecules you count, the higher is your discrimination power. For example, if I'm going to do a survey on you, if I interview 10 of you, I can tell the difference between 3 votes yes versus 4 vote yes, which is a 10% difference. Okay, 3 out of 10 versus 4 out of 10. But if I interview 100 of you, I can tell the difference between 33 and 34, which is 1% difference. So the more people I interview, just like when you're doing a survey or census, etc., the higher is the sample size, the more powerful is the statistics. And we calculate at that time, if I want to detect a fetus whose DNA is present at 5% and who has Down syndrome, I need to count 100,000 DNA molecules. So when we published this work in PNAS in 2007, many people thought that we're crazy because does it mean that you have to do 100,000 PCR per test? But that is what the statistics show. But interestingly, with the advent of next generation sequencing, suddenly it becomes very easy to count millions of DNA molecules. So each of those sequencer can sequence your genome several times, or now even 20 times in the latest generation machine. So basically what we do is one of those machines, you can see all those dots. Each of those is one DNA molecule cluster. And then in one go, I can sequence hundreds and millions of those dots. So basically what we do is that we obtain the blood plasma, and insert in there, there's some DNA molecules floating around. And then you use the DNA sequencer to sequence many of those molecules. And because we know the human genome sequence, I can use a computer to tell me where does each of those molecules come from which chromosome. And then I can plot the proportional representation of each chromosome in plasma. So in other words, for every chromosome, we can ask, what percentage of the molecules in the plasma that I sequence is from that molecule? So I can plot a histogram like that. So chromosome 1, 2, 3, 4, 5, etc. to 21, 22, X and Y. And then the y-axis is the percentage. So chromosome 1 is the longest chromosome. They represent 8% of the genome. and then gradually the chromosome gets smaller. And chromosome 21 is a very small chromosome, only about 1.3%. And X and Y are the sex chromosome. So what are those color bars? Those color bars are the plasma from a number of individuals. So one series, which is this color, is the plasma from a woman carrying a female baby. And the 2 series is the mother's plasma from a woman carrying a male baby. And the 3 series is an adult male plasma, like from my own. So the most interesting thing is over here, if you're a man like myself, you can see the Y chromosome in your plasma. But I can also see the Y chromosome from a baby boy in its mother's plasma, over here. If a woman's carrying a baby girl, then I see nothing. But the most interesting thing is on chromosome X. When you can see the dosage of X in a man is half of that in a woman, because we're XY and a woman is XX. But the most amazing thing is if a woman is carrying a baby boy, which is over here, then the level of X in her blood is lower than that of a woman carrying a baby girl. The reason is because this is XX from a mother plus XY from a baby. And this is XX from a mother plus XX from a baby. So the level of X is higher. When I see this data, I know that we have cracked the problem, because here shows you that by sequencing a mother's plasma, I can tell you how many chromosome X the baby has got. If I can do this for chromosome X, then theoretically I can do it for any other chromosome, like chromosome 21 for Down syndrome. So then we decide to use this for chromosome 21. So we decided to use a very simple statistic using something called Z-score, which is basically to measure the chromosome 21 percentage in a particular case, and then compare it with a group of control, and then ask how many standard deviations your case is compared with control. If there's no difference, then the SD will be fluctuate around 0, which is like here. On the other hand, if the baby has more chromosome 21, then the SD will shoot up, like here. So we will use free SD as a cutoff, which is over here. And then we decide to test on a number of cases. And interesting, when I test on the cases, I find that we have some cases in green and red. The Z-score are very high. As it turns out, those cases the baby have Down syndrome, which is also called trisomy 21. On the other hand, the cases in orange and blue, the SD is fluctuate around 0. So those, the babies are normal. So basically, in this initial study, we look at 28 cases, and half of them have Down syndrome and half are normal. And we have 100% accuracy. And we can do it as early as 11 weeks. So that's very encouraging. So we published this in 2008. And after that, we thought that it's so encouraging that maybe we should do a large-scale validation study. So we actually collaborate with 8 hospitals in Hong Kong, and 1 center in London, Kypros Nicolaides Group, and 1 center in Amsterdam. So in total, we look at 753 cases, in which 86 have Down syndrome. And the result is amazing. So we're able to detect every single one of the Down syndrome cases. So sensitivity is 100%. For babies who are normal, we have a 98% accuracy or specificity in detecting that. So this work was published in the British Medical Journal in January 2011. And since then, many people have reproduced this work. So to date, in the literature, there are over 20,000 cases published, and the sensitivity and specificity are generally over 99.5%. And the latest study was published in the New England Journal of Medicine about 6 weeks ago. So as a result, it's so accurate that actually this test has now been launched commercially in October 2011, which is just 10 months after we published our paper in British Medical Journal, which is amazingly fast. And we actually introduced the test to Hong Kong in December of the same year. And to date, there are about 4 companies in the US providing a test, and 2 European companies, 1 in Germany and 1 in France, and 2 Chinese companies. And actually, so now this test is available in over 50 countries around the world, including in the Middle East, and about 700,000 cases have been done just in 2 years, which is quite amazing considering this is such a complex test. And because of its popularity, this test has now been endorsed by a number of professional bodies, like the American College of Obstetricians and Gynecologists, which endorse the use of this test for high-risk pregnancy. And very similar guidelines has been issued by the American College of Medical Genetics, ACMG, and also by the International Society for Prenatal Diagnosis, ISPD. And I'm sure that many other regional guidelines will be issued very soon. So in other words, after 40 years of work around the world, and in my case, I work on this area for over 20 years, and we've finally cracked the non-invasive prenatal diagnosis of Down syndrome. So now, basically, we have a test which is over 99.5% accurate. So the question now is how best to use it. And I think each country will have to draft up its own guidelines. So what else can we do? Now, because, for example, I'm still not ready to retire, right? So I'm thinking that what else can we do after we've done Down syndrome? Now, you're being very ambitious. You'll say, well, can we sequence the whole genome of the fetus by looking at a drop of mother's blood? So we've been thinking about this problem ever since we did the Down syndrome work. And we thought that this is a very tough problem to crack. Because the fetal genome is fragmented into millions of pieces in the mother's blood, it's like you're trying to do a jigsaw puzzle with 1 million pieces. And also to make life more difficult, because most of the DNA in mother's blood is the mother's. It's like before you start the jigsaw, I put in 10 times of another jigsaw, and they ask you to start with the first one. So initially, we thought it's far too difficult to do. Until one day, I went to see this movie with my wife, which is Harry Potter. And this is one of the first movies in IMAX 3D. So I remember I'm in the darkened cinema like what you are now, put on my 3D glasses, and then suddenly I saw the Harry Potter sign flying towards me. And suddenly my eyes was drawn to this H here, which, believe it or not, in 3D, looks to me like a pair of chromosomes. And then suddenly I had an inspiration about how to crack this. I remember my wife was sitting next to me, and I told her, I think I've cracked this. And I spent the next 2 hours thinking about that. So what I realized is this, is the baby, for every chromosome the baby has, it has one copy from a father and one copy from a mother. How about if I crack the two halves separately? So what I mean is this, imagine this is the father's genome, and this is the mother's genome. The baby will have one half from father and one half from mother. So now you go into the mother's blood, there's a lot of the mother's genome floating around, and then you're trying to hunt for the fetal genome. So first, to crack the father's half of the fetal genome. So you compare the father's genome with the mother's genome, and then try to find things which is only present in the father's side, but absent in the mother's side, but which is easy to find, like the flower. And then you go into the mother's blood, and then you hunt for the flower. So provided you have enough of those flowers and zip them together, you crack the father's half of the fetal genome. So very simple. But how about the mother half? The mother half is more difficult because the fetal DNA is swimming in this ocean of the mother's DNA. So by definition, anything which the mother gives the baby, the mother will have it herself. So you cannot find a flower which can differentiate the mother from fetus. So instead, you have to do something cleverer. So what it means is this. Imagine, look at the mother's genome, the left-hand half and the right-hand half should be present at a ratio of 1:1. So now imagine the mother passed the right-hand half to the baby, and then the baby released this back into the mother's blood. So inside the mother's blood, there should be more right-hand half compared with left-hand half. So basically what you do is go into the mother's blood, and then you count the number of halves. The half which is in excess is a half inherited by the baby. And that's the theory. Of course, to do it for two halves is easy. To do it for millions of halves and put them together, it's more difficult. But that's the principle. So we decided to see if this principle works. So we recruited a couple who are both carriers for beta thalassemia. Then they come to see our obstetrics clinic, and the mother's 12 weeks pregnant, and she wants to know if the baby is normal or not. So we took blood from the mother and then do the DNA sequencing to count those molecules. That should show you how difficult this project is. For Down syndrome tests, you count 10 million molecules and you're done. But for this one, we actually have to count 4 billion DNA molecules. When I did this study, it actually cost me $200,000 US for this one case, which is probably one of the most expensive cases ever investigated in Hong Kong. But in the end, this is the result. So this is a circles plot in which the chromosomes are plotted like a circle outside, and then the blue signal is the fetal DNA, and the red one is the mother's DNA. So you can see basically the whole genome of the baby is present in the mother's blood. And also if you look at the blue and red signal, they seem to go up and down together. That means there's a constant concentration relationship between the fetal DNA and the mother's DNA. And indeed, you can actually measure the fetal DNA concentration across the different chromosomes, and you can see it's very constant, 11 point something %. So now, with this whole genome in our computer, I can just scan it for any genetic disease. For example, beta thalassemia is caused by mutations in the beta globin gene on chromosome 11. So you can just zoom into that region, and lo and behold, the baby is a carrier of beta thalassemia. So this work was published in Science Translation Medicine, and they actually chose it to be on the cover. And then about 1 year later, there are two groups in the US which actually confirmed the data. So first group published in Science Translation Medicine, the second group published in Nature. And recently, there's also another paper from China. So now the 4 groups have successfully sequenced the fetal genome from the mother's plasma. So as you can imagine, with this sort of development, there are bound to be some very important ethical, social, and legal issues. Now, for example, when we published our fetal genome sequencing paper, the Times newspaper in London actually did a front page cover on that, talking about a breakthrough in this area, but also warned about some of the ethical issues. For example, some other people, like Scientific American, thinks that we have gone too far. Maybe there's too much information from pregnant women, because imagine there are 20,000 genes in the human genome. Can you reasonably explain to an average pregnant woman which gene could go wrong? And actually, Nature have a 3-page article warning about getting ready for this flood of fetal gene sequencing. So what are some of the issues we need to worry about? Now, for example, the central thesis of this technology is that allow us to detect fetal abnormalities safer and quicker and earlier. So some people are worried that if that happens, you might increase the number of women going for prenatal diagnosis. And as a result, some people worry maybe somehow you might increase the abortion rate. And some other people also worry that if governments start to do more increased prenatal screening, they might spend less money on treating the people who are affected by disease. So they worry about the rights of the disabled. And also, another issue is the technology is still quite expensive. So now, for example, in the US, the test will cost more than $1,000. So who is going to pay for the test? Now, for example, we have surveyed the early adopters of the technology in Hong Kong, and we find that about 70% of them have got university education or above, and about 70% of them has a monthly household income of over $7,000. So clearly now, the technology is being used by the better off, the wealthier in the Hong Kong population. So what about the equity, the equality of people in Hong Kong? So we're now trying to persuade the government of Hong Kong to introduce this service free of charge to all citizens of Hong Kong. And I hope they would respond soon. Another issue we have to think about is with the increased commercialization of the field, would some company decide to directly market the technology to consumer? Now, for example, a quick search on the internet, you can see some companies are launching sex detection service using this technology. For example, like this company, which even quote our Lancet paper in '97 saying the science is proven. And some other companies elsewhere have actually decided to use this for paternity testing, like this toll-free number in the US called Are You My Dad? Right? And they say that the test, only sampling from the mother's blood is needed, and no blood is taken from the alleged fathers. So clearly now is a time for us to discuss, is that how we wish this technology being used? And is that any guidelines would be needed? So you can see how this field has developed. So basically, I've been working in fetal cells for many years, and it doesn't work. And then I saw a paper talking about tumor DNA in plasma, and that inspires to look at fetal DNA maternal plasma. And now, with that, we have really cracked a number of areas. So we thought, with the success we have with fetal DNA maternal plasma, maybe now is a time to look at what we can do back in the cancer field. So for example, if I can sequence the fetal genome from the blood of a mother, then the question is, can I sequence the cancer genome from the blood of a cancer patient? So we decided to look. And initially, we decided to look at liver cancer because in Hong Kong and in China, 10% of citizens are carriers of chronic hepatitis B. Now, for example, you sequence a tumor genome, using a tumor tissue itself, you can see some areas which are amplified with increased copy number, those in green, and some areas which are deleted in red. But the question is, if you take a blood from this patient and sequence it, can you see the same thing? The answer is yes. By using our technology, you can sequence the plasma before surgery and can basically see the same change as you can see in the tumor tissues. And after surgery, you can see that most of those changes have normalized. This is one case. This is another case which is very similar. You can see the blood before surgery and blood after surgery. And this is a third case. But on the other hand, if a patient is just a healthy hepatitis B carrier without liver cancer, then the signal is very clean. And also, you can also use this technology for other types of cancer because all cancer are basically a genomic disease. For example, look at breast cancer. You can see a lot of abnormalities. Lung cancer, smooth muscle sarcoma, neuroendocrine tumor, nasopharyngeal cancer. So virtually any cancer we use, we can actually use this technology. And this work was just published in PNAS in November last year. So in conclusion, hope I've convinced you that plasma DNA is a very powerful platform for molecular diagnostics. With this, non-invasive prenatal diagnosis is already a clinical reality. But of course, there's a lot of ethical, social, and legal issues we have to think about. And also, those technologies can also be applied in other fields, like oncology, in which we have developed a universal test for cancer. You can also use it for transplantation as well, which we can discuss later on. And finally, just a few words for some of in the audience who are medical students or the younger scientists, is that if you want to do good research, you should not rely on established wisdoms. For example, when I first started off, people would tell me the mother's and the baby's blood circulation are separate. But interestingly, they are not completely separate. And secondly, you should look in the non-obvious places. For example, like when I first started, it is really a heresy to talk about DNA present outside cells. And yet, there are actually plenty of DNA molecules swimming in our blood. And also take unconventional approach. For example, who knows, by cooking the blood like you cook noodles, you can actually crack this phenomenon. And also, you should be confident. For example, like my first case report about hemangiosarcoma, even a medical student can contribute. And also, science is very competitive. You're competing with worldwide. It's like you're going on Olympics every day. And finally, it could be very fun and meaningful because you can see I have a lot of inspiration from daily lives, from watching movies, and they can also help patients. And of course, science is a group endeavor, so I'd like to thank my team for working with me for the last 17 years for presenting the data which I've shown you today, and my various local and international collaborators. So thank you very much for your time today. Thank you.
Okay, thank you very much. That was really very interesting and exciting talk. Now it's discussion, questions, answer directly to the professor.
Yes.
Can I?
Yes.
Does the mother produce antibodies to the DNA, circulating DNA of the fetus?
Not that we know of, although at the moment I'm actually looking into systemic lupus, with, of course, you know, that anti-DNA antibody is one of the hallmark. So it will be very interesting to see what happens in that scenario. But all I can tell you at the moment is that in systemic lupus, we have a surprisingly high concentration of DNA in plasma, about 10 to 100 times higher.
I just want to congratulate you on this work, Professor, and this is very exciting. This just reminded me with the first presentation I attended in the US for one of the fetal interventionalists there. It was something like coming from the from the space. Now, can I just ask you a question? And this is more of a futuristic approach. Now, you mentioned something about the concentration of these DNAs and the way that you go as you go in the pregnancy itself. You know, I want you please to put that in context with the ethical and social things. Like if we detect something early, the intervention probably will be amenable. And I'm thinking about something that we can intervene in order to change something in the future rather than just abortion. Where do you think we stand right now, and in the future, where do you think you find some real applicability for these other than diagnostics?
Okay, thank you very much for a very insightful question. Actually, your question is very timely because we actually have just published a paper talking about using the technology for congenital adrenal hyperplasia, which, as you know, is a genetic endocrine disorder in which the baby has problem with the steroid hormone pathway. And then, if the baby has that problem, then some of those metabolites will be channeled down to become male hormones, the androgens. If the baby is male, that's okay, but if the baby is female, then the baby girl will look a little bit like a boy. And you can actually treat that if you give the mother dexamethasone, but you have to do it very early, like 9 weeks or before. And now we've shown that by using this technology, we can even detect whether the baby has a mutation or not by 6 weeks. So this is a very good example of intervention. Thank you.
It is my understanding that cellular or fetal cellular DNA exists in the circulation for decades in the maternal circulation. And with multiple pregnancies, successive pregnancies, there is always the potential that you might pick up the fetal DNA from previous pregnancies. And I don't know if there is easy distinction between cellular versus cell-free DNA in multiple successive pregnancies and with sensitive techniques like NGS. Isn't that a potential source for contamination and problems?
This is a very good question, and this is the reason why I did a study on the cesarean section. Because I've also read at that time the papers about the fetal cells persisting for 27 years after delivery. As I've shown you, the cell-free DNA is a different phenomenon, that after 2 hours, the DNA is gone. And the reason is because if you look at the cell persistence paper, they would typically require you to take maybe 20 mils of the mother's blood and then sort for some stem cell like CD34, those cells. And then even after you have done a lot of sorting, you're only talking about a very small number of cells. But whereas in the cell-free DNA, because of this very rapid turnover, the baby really have to push out about 20,000 genomes per minute to keep the level going. So basically you cannot see that. So one take-home message is that the stem cells persist because they do not die, whereas the cell-free DNA are there because the cell die. So that's why they're different phenomena.
Thank you. Thank you really very much for your very interesting lecture. And I just want to know, to tell you that we start using this technology in this hospital. In fact, this week, we in fact, as a screening for everybody nearly. As if you, I think in Royal College recommendation, the British Royal College recommended to be used for nearly for everybody, not for high-risk pregnancy. And we're trying it. My question is, can we use it for, and now we do probing for single gene mutation. Do you think in the future will replace the probing for single gene mutation?
Yes. So,
So
my paper about the congenital adrenal hyperplasia was just published in the Journal of Endocrinology and Metabolism. And you look at that particular model, it can be applied to any genetic disease in which there's a family history.
Mm.
Yeah, so like thalassemia or any other endocrine disorder. So the answer is yes.
Do you think it will be more expensive, less expensive than the present technology? This is another question, of course.
You mean less expensive than Down syndrome? Or?
Yeah. No, for single gene mutation. If you target sequencing or something like that, do you think it will be cheaper, or the present technology is what we're doing now is this?
What you're doing now at the moment is likely to be invasive, right? Based on
that's right. Yeah, that's right. Yes.
Or chorionic villus sampling.
Yeah.
Yeah. So it will be a bit more expensive than that. But it's also based on targeted sequencing. Mm-hmm. But because the fetal DNA is only a minor proportion of the DNA in mother's blood, mm-hmm. so you need to sequence more deeply. Now, usually you have to go for about 200x, so 200 times. Yes.
Thank you.
Thank you so much.
I would just like to ask if this DNA has a kind of function, or is just something that leaks. Does it have an effect on the mother, or is it something that leaks out of the fetus?
Now, this is a very interesting question, which at the moment is still no firm answer. Now, because on one side, we know the baby is working very hard, so 20,000 genomes per minute to push out to maintain a level. And then after delivery, it's all gone, okay? So as if you need it during pregnancy, but you don't need it after pregnancy. But on the other hand, the DNA that we're looking at are fragmented. Most of them are less than 160 base pair. So initially, when I was starting on the field, I was wondering how can you have a fragmented gene, which is incomplete information, be functional, okay? And then later on, in 2008, we discovered that apart from genomic DNA, there's also circulating microRNA, which are intact in the plasma. So actually one possibility is that microRNA, as you know, can regulate gene expression. So maybe actually the baby is regulating the mother's gene expression through this pathway. But that is new and needs some more work. And of course, recently, you know about all the work on exosomes, about the cell can pick up exosomes and then have functional impact. So I think that would be a very exciting area to look at. Thank you.
Hello. This is Jeddah, Dr. Ahmed Sana. Actually, I'm a member of the IDF unit in Riyadh and doing a locum in Jeddah. Thank you very much for your elaborate talk, and I think you're widely really proud of what you did and you're doing for nature and for humanity. My question is, with doing single gene disorder, PGD, cycle reimplantation, genetic diagnosis, and probably we have exceeded 250 to 300 cases per year, which is the highest number to my knowledge in the world. As a single gene disorder. My question is, can we use the same technique for patients who got pregnant spontaneously while they are waiting their turn to do implantation genetic diagnosis apparatus? I.e., do you have any cost-benefit study in your experience to justify it in a program covering this kind of problem? Because those patients are supposed to do the PGD, but they got pregnant spontaneously. And from your experience, is there any program that exists for this matter? Thank you very much.
Thank you very much for kind words and very interesting questions. So I think that I'll answer your question in two ways. I mean, the first is not directly what you asked, but I think that this technology, non-invasive technology, is synergistic to PGD in the sense that even after you have successfully done a PGD, you might wish to know if your procedure is correct or not. So the non-invasive method can allow you to confirm. But now I'll come back to your question. You're saying that even though some individuals are waiting for PGD and they got spontaneous pregnant, then my answer is yes, you can actually use this technology very early on to detect. And from our earliest data, you can actually do it from 6 to 7 weeks, although the fetal DNA concentration is lower at that time of pregnancy. But of course, the good thing about this non-invasive nature is you can do it. If it's too low, you say, I cannot give you a result. And then you wait another week and then do blood sample again. And only make a diagnosis when the DNA concentration is high enough. Thank you.
Okay, any more questions from Jeddah? If not, I just have a last question. Who is asking more? How about the RNA that's released? Have you worked on quantifying RNA? The RNA will be a direct measure of the gene expression activity of the fetal.
Yes.
In terms of cancer, will be great to study.
Oh, yes, yes. I think this is really a fascinating field. We're only scratching the surface. So yes, so we have now been able to detect genomic DNA, microRNA, messenger RNA, long non-coding RNA, or even the cancer and the fetal epigenome from plasma. Exactly. So basically, I think that it will be very exciting development in the years to come.
Fauzan, you were having a question at the beginning.
It was similar to Edward's about what that DNA circulating.
That's why you stopped resisting. Okay, with that, thank you very much. We appreciate your talk. Thanks to the audience for listening.